Before we talk anything about thermodynamics, I want to take some time to just talk about a pure math topic. Specifically, we need to talk about partial derivatives. To be precise, let's consider a variable. So let's say we have a variable x that is a function of other variables. If we consider the case where x is only a function of one variable, so let's say that variable is y, then if we just took the derivative of x, its derivative would be what we call a total derivative. Total derivative. So that's just telling us that x is only a function of y, right? And so its derivative is also only a function of y, okay? But if x is a function of more than one variable, so let's say it's a function of both y and z, its total derivative wouldn't be the function of one thing, of just one thing, but its total derivative is going to be the sum of what we call its partial derivatives. Okay? And so the way that we express that mathematically is we say that the derivative of x is going to be equal to this. dy plus dx dz y dz, and there should be a z here. Okay? So I just want to explain the notation that I'm using. So these curly d's, those indicate what we call a partial derivative. And the variable that's outside the parentheses here, this is a variable that's being held constant. And so essentially what we're saying here is that the derivative of x is going to be the sum of the function x taken, or its derivative taken with respect only to y. So we take the derivative of the function of x only with respect to y, while holding z constant. Okay? So that's what this first term refers to. And then the second term is where we take the derivative of x with respect to z, where we hold y constant. Okay? Right? And so that's all the partial derivative thing is saying here. That if we took the total derivative of x, what we would do is we would first take the partial derivative of x with respect only to y, while keeping z constant, and then we would take the partial derivative of x with respect to z, while keeping y constant, and then we would add those two derivatives together. And that's all this. That's all the total derivative of x would be. Okay. All right. Now I just want to concentrate a little bit more about what the properties are, and what are some basic things that we could do with these partial derivatives. Okay. So some basic properties of partial derivatives. And so, if we have partial derivative of x with respect to y holding z constant, that's going to be the same as saying that we have the reciprocal of the partial derivative of y with respect to x while holding z constant. So once again, you can kind of think of these partial derivatives kind of like fractions, right? And so this is equal to 1 over the reciprocal. Okay? All right, another thing is that if you took the partial derivative of x with respect to x, holding z or y constant, once again, think of them like fractions. These dx's would cancel. And what you would get is that is equal to 1. Another important thing is that if we said we took the derivative of x with respect to y while holding x constant, that would be equal to 0, right? Because it's saying that x is constant, so if we took a derivative of it, that derivative would be 0. Okay? And so these are all sort of basic, straightforward properties of partial derivatives. But using these very basic properties, we could also look at some more complex properties of partial derivatives as well. Okay? So for example, if we go back to equation 1 here, let's take the derivative of it with respect to y while holding x constant. Okay? And so if we differentiate 1 with respect to y holding x constant, okay, so what we would have is dx dy constant x is equal to dx dy constant z times dy dy constant x. And so essentially you could kind of think of it like we divided everything here by dy. Okay? Yep. So we have that, and then we have dx dz constant y dz dy constant x. Okay? All right, so this is what equation 1 turns into if we take the derivative of it with respect to y while holding x constant. Right. And so here, if we look from left to right, we have dx dy constant x. That means that this part is equal to 0. Here we have dy over dy constant x. That means that that is equal to 1. Okay? And one other thing that we could do is here we have dx dz a constant y. Using this little reciprocal rule that we have, we could also say that this is equal to 1 over dz dx a constant y. Okay? All right, in any case, with applying these three basic properties, we could rearrange this equation. So just to be clear, this is equal to 0. We could rearrange this equation so that we get that dx dy constant z times dz dx constant y is equal to negative dz dy at constant x. Okay? And so what you kind of see here is that, with those three variables we have, we're basically kind of cycling them into the three different places. And so x and z switch places, and then y goes out here, or I guess you could kind of think of it as like a little cycle. So z goes here, x goes here, y goes here, and that gives us here this. And yeah, and so that's essentially what we have. And so this identity that we have here, you could play around with it some more to rewrite it. But essentially what we have here is the triple product rule. Okay. So this is just another identity of partial derivatives.